Okay, so let us begin with today's lecture, and today we will be studying graphs. So let us start with a motivating question. So this is the famous Königsberg Bridge problem. So Königsberg was a city in Russia, in Prussia, and Prussia is basically it overlaps quite a bit with what the country that we know as Germany today. But Königsberg was sort of in one of the certain part of Prussia, which is now actually included in Russia, in modern Russia. And the city of Königsberg is in Russian is known as Kaliningrad today. But around the 1700s, the city of Königsberg was in Prussia. And the citizens of Königsberg, which is a beautiful town actually, they would so the city of Königsberg had a particular structure. So there was some river going sort of traversing the city, and there were some islands and there were some bridges connecting the islands and the two banks of the river. And an interesting question to some of the citizens of Königsberg was to walk around the city, crossing each of the city's 7 bridges exactly once. Okay? So the point is that you will traverse the various parts of the districts of the city, but the restriction is that, in order to do that, of course, you have to cross the bridges, because there are certain parts of the city where you cannot get to some other part without using one of the bridges. So of course you have to cross the bridges, but you are allowed to cross. You are not allowed to sort of retrace any bridge. So you are allowed. You want to cross every bridge once and only once. Okay, so that's the kind of constraint. So of course that this kind of constraint forces you to choose your path through the city cleverly. So the question is whether this is at all possible or not. Okay. So here is a diagrammatic representation of the 7 bridges of Königsberg, and here is a further simplification of an even more simplified diagrammatic representation. So what is the reason of bringing the story of Königsberg and its bridges in the context of graph theory? Because in our study of graph theory, essentially it is this kind of pictures that we will be concerned with. When we study graph theory, it is customary to recount the name of another, just like the famous city of Königsberg. We have to recount the name of a famous personality in the history of mathematics. It's the name of Leonhard Euler or Leonhard Euler. Leonhard Euler was born in 1707 in Basel, Switzerland, and passed away in 1783 in St. Petersburg, Russian Empire. So he lived a substantial portion of his life in Russia and did mathematics there. So Euler was he was like a very versatile mathematician. So he made contributions to almost all areas of mathematics in which people were interested in those days. So back in those days, mathematics was a much smaller and simpler subject, but within that smaller and simpler subject, Euler contributed to almost all possible domains of mathematics in those days. So this includes the study of graphs, and we start with discussing what is an Euler walk on graph. Before that, let us discuss a bit about what we mean by a graph. A graph is essentially a bunch of nodes like this, and some of these nodes are connected to each other by an edge, and some of the nodes are not connected by an edge. Okay? So, it is a bunch of nodes with some edges connecting some of them. Okay? So, this is what a graph is, and an Euler walk on a graph is a walk. So, a walk means a path which traverses the edges of the graph. So, an Euler walk is on a graph is a walk that uses every edge in the graph exactly once. So, now you can easily connect this concept to the Königsberg bridge problem, because if you represent the Königsberg bridges like this, you want, so these are essentially the bridges, and basically what you want is that you want a walk on this graph which traverses every edge, that is every bridge exactly once. So, that is the correspondence. So there are two kinds of Euler walks, a closed Euler walk or an open Euler walk. So, what is a closed Euler walk? A closed Euler walk is that you start from a point in the graph and you traverse, in your walk you traverse each edge of the graph exactly once and you return to where you started from. So, this is a closed Euler walk. It is naturally closed because you form a closed loop in your walk. An open Euler walk is a walk which starts and ends at different vertices. So, you start from certain vertex, walk around the edges of the graph such that you traverse exactly once every edge, and then you end your walk at a different vertex compared to where you started from. So, that is an open Euler walk. So, in summary, what is an Euler walk? An Euler walk is a walk that is a route, a path traversing the edges of the graph. It is an Euler walk if you pass every edge exactly once, every edge in the graph exactly once. And and an Euler walk is closed if you start and end at the same point, forming a closed loop, and it is open if you start and end at different points. So, it is like an open path. Okay. So, let us now record the definitions of graph, edge and walk more precisely. So, graph is a collection of points and lines connecting some pairs of points. Okay. So, exactly as we discussed, you have a bunch of nodes or points, and some of the pairs of nodes are connected with each other by an edge or line, and these connecting lines between pairs of vertices are known as pairs of nodes are known as edges, and the nodes are known as vertices. And but edges are not present between all pairs of vertices. Okay, so there are some pairs of vertices which are connected by an edge, some pairs which are not connected by. So here in this picture, here is a picture of a graph. So the vertices are A, B, C, D, and E, and the edges are AB, BD, BE, CD. CE and DE. Okay. So these are all the edges connecting to this. Any questions? You can also so in a graph, it's really about the vertices and the information that which pairs of vertices are connected with each other. So it doesn't have to do so much with how you draw it on your with pen and paper, right? Okay. So for example, this is a graph, and you can also draw it in this manner. It might look a little different, but essentially it's the same graph, because by what we understand by a graph are the information about the nodes of the graph, what are the nodes of the graph, and information about which pairs of vertices are connected by an edge. That's all. Okay. So the specific visual or pictorial representation doesn't matter so much. Okay. So, two vertices which are joined by an edge like C and E here are called adjacent vertices, right, because you can go from one vertex to another just in one step. So, here are some examples. So, here is a simple graph. So, a simple graph is before understanding what are simple graphs, it's easier to understand what are not simple graphs, and then we will just define simple graphs by complement. So, the point is that if you look at the definition of graphs, then technically it doesn't exclude the possibility that there can be loops at certain points, or certain pairs of vertices can be connected by multiple edges. Okay? So, this possibility might be there depending on the nature of your graph that you are studying. Of course, this makes life complicated because if there are 2 points and there are 2 different roads or 2 different edges connecting the same pair of points, then of course it increases the number of possibilities and therefore the number of complications much more. So, those are in some sense complicated graphs, and what we would like to focus on are simple graphs which are devoid of those complications, namely devoid of loops or multiple edges. No loops and no multiple edges. Those are simple graphs. Okay? Any questions? So, here is a popular example of graphs. So, these are graphs which can be obtained from Facebook or any other social networking site. So, on a social networking site, you can imagine, like Facebook, you can imagine the different vertices who are people who are users of Facebook. Okay? So, they are the vertices of your graph, and you say that 2 vertices are connected by an edge, that is 2 vertices are adjacent on Facebook if they are friends on Facebook. Okay? So, that defines a perfectly legitimate way of defining when 2 vertices are connected by an edge, and this gives you a graph. So, we can think of Facebook as a graph whose vertices are people and edges are some kind of social or person to person relationship. So, for example, on Facebook, the concept of being friends on Facebook. And the graph can, for example, help us decide if someone is more influential than the other. So, for example, if there is a particular vertex which is on Facebook, there is a particular user who is friends with a lot of people. So, if you translate this in terms of graphs, there will be a lot of edges, there will be a lot of vertices sharing an edge with this particular vertex. So, in that case, of course, the vertex which is adjacent to a lot of other vertices in the graph, in terms of Facebook, a user who is friends with a lot of other people on Facebook, of course, they are influential in a social media or social networking sense. Okay. So, now let us introduce the terminology that we discussed a bit hand-wavily slightly earlier. So, we will discuss about walks, we will discuss about paths, cycles, degree of a vertex, and so on. So, a walk and a path. A walk is a sequence of vertices and edges in a graph such that the sequence alternates between vertices and edges, starting and ending with vertices. So, you start from a vertex, traverse an edge, go to another vertex, then you traverse another edge, go to another vertex, and so on, and you end at some vertex. Okay? So, this is a walk, the natural notion of what you would think of as a walk on a graph. And a walk that starts and ends at different vertices is called an open walk. A walk that starts and ends at the same vertex, so some closed loop like this along the edges of the graph, is called a closed walk. And a walk that contains no repeated vertices and edges is called a path. So, So exactly like this, you do not repeat any edge or vertex. So it's a path. So let's take an example. So A, B, so A to B, B to C, C to E, E to B, B to D is, so you can put arrows in order to say who follows who. So is simply this is a walk which starts at A and ends at D. So let's take another example. A to B, B to C, C to B, B to E, and E to A. Okay. So this is a closed walk, right? Because it starts at ends at A. But this is not a path because the edge BC is traversed twice. Okay. So let's now see an example of a path. The walk A to E, E to B, and B to D is a path because it doesn't repeat any edge or vertex. Okay. So what is a cycle? A cycle is a closed walk, so it starts at ends at the same vertex, but the only repetition is the first and the last vertex. So since the walk starts at ends at the same vertex, therefore of course it's not going to be a path because of course the starting vertex is repeated because the starting vertex is the same as the ending vertex. However, that's the only repetition that is allowed. Okay. So that kind of a walk, that kind of a closed walk is called a cycle. So it will look like something like this. So you traverse, and the only repetition is the starting and ending points. Okay. So here, for example, in this graph, there are 3 cycles of length 4. So for example, one of them is A to B, B to D, D to E, E to A. Okay. Similarly, you can find other cycles. So there are 3 cycles of length 4, and these are A, B, C, E, A, B, D, E, A, which we discussed, and also B, C, E, B, D. Okay. Sorry. B, C, E, D, B. Exactly. So B, C, E, D, B. So of course it starts at ends in B, but other than that, there is no repetitions. So here is another example. You look at the same graph. We say that we claim that there is no cycle of length 5. What is the reason behind that? So since if your cycle has length 5, then of course the starting and the ending vertex has to be the same. So the length of a cycle is the number of edges, right? So the start and end of the cycle has to be the same. So there has to be 5 vertices in total, right? So since there are only 5 vertices in the graph anyway, so the cycle must traverse all the 5 vertices. Okay? In particular, it must contain A, C and D. Okay? So notice that there are no edges between any of these vertices. So there is no edge between A and D, no edge between D and C, no edge between A and C. So of course, if it contains A, C and D, then the graph has the cycle has to enter A at some point and exit A, right? So the cycle, if you traverse the cycle must contain A because it contains all the vertices. So when it comes to A, it must come via certain edge and depart from A via certain edge, right? So a cycle must contain both AE and AB, right? Because there are only 2 edges which contain A. So the cycle must enter along one of these edges and exit along the other. Similarly, the same can be said about C. So there are only 2 edges which contain C. So the cycle must contain both edges because the cycle must enter C by one of these edges and exit C by the other edge. The same can be said of D. So the cycle must contain both DE and DB, which are the only 2 edges incident on D. But you notice that if you draw any 5 cycle, there are only 5 edges. Whereas here you have already accounted for at least 6 edges which must be inside the cycle. So if there was a 5 cycle in this graph, a cycle which traverses all the 5 vertices and and without any repetition of edges, then of course this is not possible because such a cycle can have only 5 edges, whereas if such a 5 cycle had existed for this particular graph, then by natural logic all these 6 edges must be present, so the cycle must contain at least 6 edges. So this is not possible. Okay? So by a slightly complicated and tricky argument, we found out that this graph cannot contain any 5 cycle. Any questions? So here is another concept. This is the notion of the degree of a graph. So degree of a vertex in a graph. The degree of a vertex in a graph is the number of edges that occur at that vertex. Okay? And if you are considering not a simple graph, then you might have loops. So you count every loop as 2, one for exiting and one for entering. Once for exiting and once for entering. But if you find this complicated, then you can just focus on simple graphs. So that's what we will mostly be concerned about in this module. So degree of a vertex is a graph in which is the total number of edges that occur at that vertex. So let us try to understand the concept of degree using the example of the Facebook graph. So in a Facebook graph, remember the nodes or the vertices are the Facebook users and the edges are the relationships of being friends between any 2 users. So what is the degree of a vertex? The degree of a vertex is the total number of edges which are sort of containing that vertex. So in particular on the Facebook graph, since an edge denotes friendship, therefore the degree of an edge is the total number, the degree of a vertex on the Facebook graph is the total number of friends of that particular Facebook user, right, on Facebook. Okay? Is it clear? So whenever 2 people are friends on Facebook, you draw an edge between those 2 people. So if you focus on a particular person, a particular Facebook user, and look at the total number of edges which are occurring at this particular vertex, then all of these are friends of that particular user. So the degree of a vertex on the Facebook graph essentially counts the number of friends a person has on Facebook. So, look at another example. So, this is degree of A. So, this is this particular graph. So, the degree of A is 2, degree of B is 4, right? 4 edges are emanating out of it. Degree of C is 2, degree of D is also 2 because there are 2 edges which occur at the vertex D, and degree of E is 4, so because there are 4 edges which occur at the vertex. Okay. Any questions? So, here is a very basic result. So, this is the degree theorem. In any graph, the sum of all the degrees is twice the number of edges. So, you just go, so every vertex has a degree, right. So, to every vertex you attach an integer which is the degree of that vertex. Now, what happens if you sum up all these integers, you sum up all these degrees over for the various vertices? The answer that you will get will exactly equal 2 times the total number of edges in that graph. Okay. So, how do you see that? Actually, this is a very simple simple idea. So, think of the Facebook graph. If you think of the Facebook graph, then every edge denotes a friendship, right? So, now let us count the number of edges and keep in mind the number of vertices. So, if you think of the degrees and if you sum the degrees, then when you are at this particular vertex, so think of a situation like this. Maybe this is another vertex, so this will have another, wow. Okay. So, let us focus on these 2 vertices. So, you are summing the degrees over all the vertices. So, when you look at the degree for this particular vertex, you are basically counting 1 for each edge which is incident on this vertex, right. In particular, you are counting 1 for this edge. Okay. So, let us call this vertex as V, this V1, this vertex as V2. So, when you are looking at degree of V1, this particular edge, let us call it E is counted once. Counted once, right? Because you count every edge that is incident on that vertex once. If you are now, let us look at V2. So, if you look at degree V2, and again you just put 1 for all the edges of the graph that are occurring at the vertex V2. So, then also the AG is counted once, right, because again you are counting 1 for every edge which is originating at the vertex V2 or which is occurring at the vertex V2, right. So, now when you are summing these 2, the edge E is being counted twice, right. So, if you and the AG only contains the vertices V1 and V2. So, when you look at the vertices, when you look at the degrees of other vertices, the AG will not come up in the calculation. So, when you are summing the degrees of V1 and V2, if you just focus on what is happening to the contribution of the AG, it is coming up twice. Similarly, and this can be said of any edge in the graph. So, if you sum up all the vertices, if you sum up the degrees of all the vertices in the graph, then every edge in the graph will be counted twice. And therefore, the sum of all the degrees in the graph will be twice the number of edges, because we have just seen that when you sum up the degrees of a graph, then every edge is counted twice, once for each endpoint of that edge. Okay. Any questions? Okay. So, back to Euler walks. An Euler walk in a graph is a walk that uses every edge in the graph exactly once. So, you are doing a walk. So, you are traversing the edges of the graph by walking from one vertex to another. And an Euler walk is a walk which is such a walk which uses every edge exactly once. And we already noted that a closed Euler walk is a walk which starts and ends at the same point. It's an Euler walk which starts and ends at the same point. So, you start from a point and you traverse all the edges of the graph exactly once, and then you end where you started. And an open Euler walk is you start from a vertex in the graph and traverse all the edges of the graph exactly once, and then you end at a different point, different from where you started from. Okay. So we will consider simple graphs first, and we will also be focusing on what are called undirected graphs. So you don't have to worry about this concept right now. It will come up again as usual. It will be easier to first understand what are so-called directed graphs, and then it will become clear what are undirected graphs. For the moment, just think of just simple, plain simple graphs which we have discussed so far. And then if your graph is of a particular nature like this, you can read off the Euler circuits from the blue edges. And basically you might wonder, and this is also related to the Königsberg bridge problem, you might wonder whether in a graph, so the Königsberg bridge problem can be reduced to the following question. If you represent the status of the different parts of the Königsberg town and the bridges connecting them in the form of a graph, then walking through the different parts of the town, traversing every bridge exactly once is equivalent to finding an Euler walk in this graph, right, which represents the Königsberg bridges. And so the question is whether there exists at all an Euler walk on this graph. So the question of existence of Euler walk is very important. So, but before defining Euler circuits, before stating stating a result about the existence of Euler walks, we also need to define Euler circuits. So Euler circuits are essentially you start and you are an Euler walk and you start and end at the same point. Okay, so it's a closed Euler walk. So a connected graph has an Euler circuit if and only if the degree of every vertex is even. So you will be able to start from a vertex, take an Euler walk, so traverse every edge exactly once and end at the same point, if and only if the degree of every vertex is even. Okay, if you have and if you want an Euler walk, so you start at a vertex A and end at a different vertex V and traverse every edge of the graph exactly once. This is possible if and only if every vertex of the graph, so this is the starting point, this is the ending point, every vertex of the graph has to have even degree, just like the case of closed or Euler circuit. However, the only two vertices A and B, they have to have odd degrees. Otherwise, every other vertex has to have even degree. So the starting and the ending points must have odd degrees, and every other vertex has even degree. So then you can have an Euler walk starting at a vertex A and ending at a vertex B, which is different from it. And if every vertex of the, if and only if every vertex of the graph is even, if every vertex of the graph has even degree, then you have an Euler circuit. So you can start from a point and you can come back to the point, traversing every edge of the graph exactly once. Okay. So the proofs are, of course, they are fun proofs and they are beautiful, but we will not we will so these are not for exam purposes. So let me state that first. So for your enrichment only, not to be tested. So you can so you can sort of for pleasure or enjoyment you can go through the details. So what I will do is that I will in the lecture I will sort of discuss an easy aspect of the detailed proof of the existence result for Euler's work. So this is also known as Euler's theorem, which basically, and the reason why I will discuss this argument is that it essentially embodies a certain kind of thinking which gives you the flavor of how people think in about graphs, how people think in graph theory. Okay, so this is this statement that if an Euler circuit exists, that you start from a point, start from a vertex in a graph, and you traverse each edge of the graph exactly once, and you can come back to the original point. If such a path, if such a walk exists in your graph, then you want to show that all vertices have even degree. Of course, Euler's theorem actually tells you much more. It tells you that if every vertex has even degree, then you are always going to have such a path, which is actually sort of the statement which answers for you the riddle about the Königsberg bridge problem, because if you look at the because you can solve the Königsberg bridge problem in the following manner, that you construct the graph which represents the different parts of Königsberg town and the bridges connecting them as edges, and then you just check Euler's condition, you just check the condition of Euler's theorem for this particular Königsberg graph, whether every vertex has even degree. If the answer is yes, then Euler's theorem tells you that there exists some Euler circuit, that is some path or some walk which traverses every bridge exactly once and comes back where you started from. Okay. But that's sort of the more complicated direction, and kind of it will take us a bit beyond in terms of complication, it will take us a bit beyond the level of this module. So instead what we will focus on is the statement in the other direction, which is the implication that if a circuit exists, then all vertices must have even degree. Okay. So this is going to give you the flavor of the thinking in graph theory, so that's what we want to extract. Okay. So you start from a point, so you have an Euler circuit, so you start traversing that circuit. Okay. So what is an Euler circuit? To remind you, it's a walk in the graph. So you start from a point A, you start from a vertex A in your graph, and you traverse the edges of your graph, passing every edge exactly once, and then you come, in the end, you come back to your starting point A. Okay. So you are traversing a graph, you are traversing your graph via this Euler circuit. So imagine that you have a red pencil in your hand, and you start at the starting point A, the starting vertex, and every time you visit a vertex C different from A using your walk, so suppose you are A here, maybe even the next step already is C, so you enter from A to C using this edge, then you must also leave C, right, because the Euler circuit starts and ends at A. So if you have entered a vertex C, then you must also leave the vertex C, and the edge through which you enter C must be different from the edge through which you exit C, because the Euler circuit is not allowed to repeat edges. So you enter C by an edge and you exit C by a different edge. and then you continue along your walk. It might so happen that you might come back to C again, because the Euler circuit is not allowed to repeat edges. It can repeat vertices, right? You come to C again and you leave again. But in doing so, you will use a fresh pair of edges to enter A and to enter C and exit C. You cannot use the old pair of edges to enter and exit, because those are already used, and the Euler circuit is not allowed to reuse edges, right? So for every entry, so every time your Euler circuit visits the vertex C, you have a pair of new edges, one to enter and one to exit. And for every visit to C, you have a fresh pair of edges, 2 edges every time for every visit, right? And the Euler circuit covers every edge of the vertex. So after you have taken your tour and ended up in A, and you are coloring every edge you traverse in your Euler circuit by red pencil, after you have traversed your Euler circuit and started and ended in A, you must have covered all edges of the graph by the red pencil, because an Euler circuit is supposed to cover all edges, right? So all edges have been covered, and you have noticed that for any vertex C, you have noticed that for every visit to C, you have a count of 2 new edges. So the total number of, and since the Euler circuit covers all the edges of the graph, in particular these visits to C must cover all the edges which occur at the vertex C. So all edges, in particular all edges which are occurring at the vertex C, must have been colored by your red pencil by now. And you have noticed that these edges which are incident or which occur at the vertex C occur in pairs, one for entry and one for exit for each visit to the vertex C. So definitely the total number of edges which occur at the vertex C is going to be 2 times the number of such pairs, that is 2 times the number of visits at the vertex C by your Euler circuit. So since it is 2 times an integer, of course the total number of edges which occur at the vertex C is even number. Okay? Is it clear? Any questions? Any questions? So this gives you the flavor of graph theory. So it might be your graph may be completely arbitrary, completely random, and you are not making practically any assumptions about it, but just the existence of an Euler circuit allows you to count things cleverly in this manner, and ultimately you end at the conclusion that every vertex of the graph must have an even number of edges occurring at that vertex. Okay? Okay, so this is all that we will discuss about the proof of Euler's theorem. For those of you who are interested, you are welcome to go over the details of all the other aspects of the proof, and if you have questions, you can come to me. But in the lecture, we will not go into the further technical complications of the proof of Euler's theorem. So let us take a 10-minute break right now, and after we are back, we will start again with Euler circuit and continue with further discussions on Euler circuit. Okay, so let us continue with our discussion of Euler circuit. So Euler walk in a graph is a walk that uses every edge in the graph exactly once. And Euler walk could be open or closed. So if it is closed, it's an Euler circuit. So a connected graph. So a connected graph is a graph in which every pair of vertices, maybe they are not connected by an edge, but they can be connected by a walk. So you although two vertices might not be neighbors, but you would be able to go from any vertex to any other using a sequence of edges, okay, using a walk. So a connected graph has a Euler circuit if and only if the degree of every vertex is even, and a connected graph has an Euler walk starting at a vertex A and ending at a vertex B different from A, if and only if A and B have odd degrees, and so the starting and the ending vertex have odd degrees, and every other vertex which are different from the starting and ending vertex have even degree. So here is an example. So you have the following graph. So the vertices and the edges are as described. The problem is to add the smallest possible number of edges to this graph so that it contains an open Euler walk. So the question is that you want to create a walk which starts at a vertex, ends at a different vertex, and traverses every edge of the graph exactly once. So the question is, the first question to address is, first, let us try to see if this particular graph has an open Euler walk itself. So what was the condition for the existence of an open Euler walk? An open Euler walk between two vertices exists if and only if the following condition is satisfied. So the starting and the ending vertices have to have odd degree, all the other vertices have to have even degree. Okay? So what is the problem here? You see, if you look at the degrees of the various vertices, so this tells you that when you come to the question of Euler walks, an important, or Euler circuits, an important quantity which you have to look at is the degree of the different vertices. Okay? So let's calculate the degree of the different vertices. So vertex A has degree 4, vertex C has degree 4, vertex D has, oh, I'm sorry. Vertex A has degree 3, vertex C has degree 3, vertex D has degree 3, vertex E has degree 3, only vertex B has degree 4. This is not good, right? Because even if you had an Euler circuit, then all vertices have to have even degrees. Even if you have an Euler walk, which is not an Euler circuit, you can have at most two vertices, namely the starting and the ending vertices, which have odd degrees, and every other vertex have to have even degrees. So here clearly there are 4 vertices with odd degrees. That's too much. So of course, so therefore the question of adding edges comes up. So suppose now, so let's start adding edges, right? Because clearly you need to change the degrees, otherwise there will be no Euler walk. So let's add the edge between D and E. So we will start adding edges gradually. So minimum number of edges we can add is 1. If that works, fine. If it still doesn't work, we will add more. But let's start with adding one edge. So so which vertices do you have to change the degrees? You have to change the degrees of A, B, C, or E, right? And of course, if you just by symmetry, if you just start from D, you want to change the degree of D by adding an edge. So this edge could go to A, but an edge is already there. It could go to B, but edge is already there. It could go to C, but an edge is already there. So if you want to add an edge to the vertex D, you can only add an edge by connecting the vertex D to a vertex C by an edge. So this is the only possibility if you wanted to change the degree of D. So the degree of D now becomes 4, degree of E now also becomes 4 just after the addition of this one edge. And let's now take stock of the degrees of the different vertices of this graph and see whether it satisfies the condition of the Euler's existence for Euler's walk. So this graph has 5 vertices. 2 of these vertices have degree 3 and all the rest of the vertices have degree 4. So 2 vertices have odd degrees, the rest of the vertices are even degree and the graph is corrected. So we are in great shape to apply Euler's theorem and conclude from here that indeed you can have an Euler walk for this graph without actually constructing it by hand. By using Euler's theorem, you can say that just by looking at the degrees, you can conclude that there is going to be an Euler walk in the graph. And also, you can conclude what are the starting and ending vertices. The starting and ending vertices are going to be A and C because these are the only vertices in the graph which have odd degrees. And in the theorem for Euler walk, with different starting and ending points, the only vertices which are allowed to have odd degrees are the starting and the ending vertices. Okay? Any questions? Okay. So this is the details of the solution that we discussed. So let's now come to the handshake lemma. So last time before the break we discussed the theorem that in any graph the sum of all the degrees is equal to twice the number of edges. So let's go over another avatar of the same result. So this is quite important result actually. So think of the vertices as people in a party. So similarly, similar to the in flavor to the notion where we were thinking of vertices to be individuals on Facebook. 2 vertices are connected if the relevant pair of persons shake hands. So similar to on Facebook, they are friends on Facebook. And the degree of a vertex is the number of hands that a person has shaken, right? It's exactly, so 2 vertices are connected by an edge if these 2 persons shake hands. So definitely a person will be connected to all the other people with whom he has shaken hands. So the degree of a vertex is equal to, which represents a particular person, is equal to the number of handshakes which this particular person has done in the party. Okay? At the end of the party, ask everyone how many people he or she shakes hands with. Okay? So you just count, so you ask every person for the number of handshakes he or she has done, and then add up all these handshakes for all the persons together. Okay? So the sum of everyone's answers, the sum of the handshakes which every person has done is the sum of the degrees in the graph theoretic language. But every handshake contributes a count of 2 to the LHS because every handshake contributes 2 to the total sum of degrees because every handshake will be referred to by both the parties shaking the hands. So every handshake will be counted once, first time when, so if the 2 persons A and B are shaking hands, then the same handshake will be counted twice. First when you are counting the degree of A, and then again the second time when you are counting the degree of B. So when you add up, every handshake is going to contribute twice, and therefore the total number of handshakes, which is the total number of edges, and the sum total of the handshakes done by all the person is related in the following manner. The sum total of the handshakes by all the individual people present in the room is equal to twice the total number of handshakes that have taken place. Okay? So that's why this result is also called the handshake lemma. Any questions? So here is a simple corollary of the handshake lemma in relation to the question of degrees and odd and even degrees that we were studying. So in any graph, the number of vertices of odd degrees is even. Okay? So, y, let us do a simple calculation. So, sum of our vertices v, degree of v, and this is 2 into number of edges, right. Now, the sum of the vertices v, you can classify the vertices into two kinds of vertices. One kind of vertices are those which have odd degree, the other kind of vertices are those which have even degree, right. So, you write the sum of the degrees of the vertices as sum over vertices v such that v has even degree or odd degree, degree v, and sum of degree v over vertices such that v has even degree. Okay. Now, let us do a simple parity calculation. The right hand side is even, right, because it is 2 times the number of edges, so 2 times an integer, so even. What about the left hand side? The left hand side consists of 2 parts. Let us look at this one. Sum of degree v over vertices v which are of even degree. So, if vertex v has even degree and we are only counting vertices v which satisfy the even degree condition in this sum, so then you are adding up a bunch of even numbers inside this bracket. So, this number and a sum of a bunch of even numbers is always an even number. So, this is also even, right. The right hand side is even, this bracket sum is even. So, this means that this first sum is forced to be even. Okay? But the first sum is the sum of degrees over vertices, precisely those vertices which have odd degrees. So, each of these degree v's are odd. Okay? So, you are summing a bunch of odd numbers, but your sum has to be even. When can that be possible? It is possible only if you sum a bunch of odd numbers even number of times. So, for instance, if you take 2 odd numbers 1 and 3, the sum is even. But if you take 3 odd numbers, that is an odd number of odd numbers, the sum is 9, which is odd. And this is true in general. If you take an odd number of odd integers, the sum is always odd. If you take a bunch of even number of odd integers, the sum is even. So, if you have a bunch of odd integers and their sum is even, then the total number of those odd integers in the first place has to be even. So, that is the ball game. So, this implies in particular that the handshake lemma in particular implies that the total number of vertices of odd degree is even. Okay? Any questions? Any questions? So, in particular, this means that we can always create an Euler circuit by adding new edges that pair up the vertices with odd degrees. So, since the odd number of vertices with odd degrees is even, so think of the situation, simple situation where there are only two vertices with odd degrees. Okay? So, the number of vertices with odd degrees has to be even. So, it has to be 2 or 4 or 6 or 8 or da da da. So, let us take the simplest case when there are only 2 odd degree vertices. Okay? If there are only 2 odd degree vertices, then suppose you put an extra edge between these 2 odd degree vertices, then they become even degree, right? And all the other vertices are even degree anyway. So, now you have your graph after adding this edge between the 2 odd degree vertices satisfies the condition of the existence of the Euler circuit that the degree of every vertex must be given, right. So therefore, by adding edges carefully, cleverly in this manner, you can force Euler circuits to exist. So, so this was all that we had for the moment about Euler circuits. So now we will move on to the question of directed graphs, which is also referred to as digraphs for brief. So we regard a graph as suppose you think of a graph as a network of roads. So similar in spirit to the Königsberg bridge problem. So your vertices are different localities, and your graph is just a network of roads. Okay. Of course, it's often the case, particularly if you go to busy parts of the city during the rush hours, that streets are one way. Okay, so it's not unusual to encounter one-way streets. In other words, if the street is one way, we can put an arrow on the street in order to denote the direction in which travel on that street is allowed. Such a graph with directions indicated on each edge is called a directed graph, or digraph for short. So for example, something like this. Maybe you can go from here to here, here to here, here to here, and so on. So some distribution of arrows on the edges. And we can define a walk in a directed graph naturally by only allowing walk that follows the indicator. So if you are on a directed graph, the natural definition of a walk would be to follow the arrows on the edges on which you are working, right? So that's intuitively clear. And that's also natural from the point of view of interpreting the graph, the edges of the graph as the roads in a road network. Okay. So here are some examples of walks in a digraph. So you have, let us consider this digraph in the picture. So A to B, B to C, and C to A is a closed walk. A to B to C to A to D is an open walk. And finally, A to B to C to D is not a walk, because in order to make this last step, you have to go against the arrow from C to D, which is not allowed. So this is not a walk. Okay? So just to give you the ballpark idea of how we deal with directed graphs as different from undirected graphs. So the Euler's theorem that we studied about the existence of Euler circuit or open Euler walks also has a counterpart for directed graphs, and of course for a directed graph we will only consider Euler circuits which are directed, or open Euler walks which are directed, right? So any walk must follow the directions of the arrows on the edges. So a connected directed graph contains a closed Euler walk or an Euler circuit if and only if for every vertex the number of arrows pointing in is equal to the number of arrows pointing out. Okay? So this is, in some sense, it is a generalization of the condition which we had for graphs without arrows or without directions. So for graphs without arrows, we noticed that the condition was for every vertex to have even degree. Okay, but if you look at the discussion of why that should be true, basically we paired every degree by we paired of the edges occurring at a vertex C by considering the edge through which you enter the vertex C and the edge through which you exit the vertex C for every visit to C, right? And we just chopped up, we just broke up the total degree of the vertex C in terms of those entry and exit edges in your Euler walk or Euler circuit. So here here the condition is that here you are allowed to enter into the vertex C only via an edge that points towards vertex C, and you are allowed to exit vertex C only via an edge that points away from vertex C, right? So if you again do the same argument of following the arrows and looking at the visits, focusing on vertex C and looking at the visits of your Euler circuit at the vertex C, you will realize that every time you enter the vertex C, you have to exit the vertex C. So the total number of edges at the vertex C which have arrows pointing towards C must, so these are all the entry edges, they must be equal to the total number of edges at the vertex C with arrows pointing away from C, because these are all the exit edges. Okay? So this is, it turns out that this is exactly the condition for connected directed graph to consist of an Euler circuit, which is that for every vertex the number of arrows pointing in is equal to the number of arrows pointing out. And finally, so this is the last item in the class, so in today's lecture, so we can also obtain obtain a generalization of the second part of Euler's theorem for existence of open Euler's walk in the case of directed graphs. So previously, in the previous version of the theorem, we stated it for graphs without arrows. So if your graph has arrows, that is it's a directed graph, then also you can formulate analogous condition for the existence of an open Euler walk, which is actually a generalization for of the condition for the existence of open Euler walk for graphs without arrows. But as you can see, it is substantially more complicated than the case of undirected graphs. So the statement will be for your enrichment only. So not to be tested in the exam. But basically, just focus on the part 1 and notice that for directed graphs, we are basically doing arguments of the similar flavor as graphs without arrows, and the criteria for the existence of Euler circuits or Euler walks are exactly the natural generalizations or analogues of the case for graphs without arrows. Okay? So this is all that we had for today, and we will continue in the next lecture.